Okay, everyone. So it's our last presentation today, and we have Mark Wasserman with us, principal architect in NVIDIA. Give us some intro to OpenFOAM. Mark, go ahead.
Thank you, Fear. Hi, everyone. Nice to see all of you. And so I'm going to present a few slides that give some intro into the task and about myself in general and OpenFOAM and also CFD. Then at the end, we'll have some time for questions, hopefully. Okay, so let's start with some background about myself. So my PhD was in aerospace engineering, so the field of computational fluid dynamics, which OpenFOAM actually simulates, is very close to heart. That was the topic of my PhD before I branched out to several other fields. After doing my PhD, I've worked in various positions in software research and development, starting from an intern and up to a group lead. My original expertise and something that I enjoy doing today as well was CFD applications. Among them are OpenFOAM, but also commercial variants such as Fluent, StarCCM+. And I spent over a decade in developing commercial CFD code, not open source, but commercial CFD code. But all the time that I worked on this, I was also deeply involved in optimizing OpenFOAM performance. As part of my OpenFOAM is an open source code, and as part of my role in the community, I also co-organized the OpenFOAM HPC challenge, which the test case that is presented in the SCC competition comes from. It was extensively studied in the OpenFOAM HPC challenge, and we'll touch on that a little later. So I'm also a member of the OpenFOAM HPC technical committee, which is a committee also of volunteers from various industries and companies that is dedicated to accelerating OpenFOAM in terms of suitability for heterogeneous hardware and high-performance computing. But I'm also involved in other open source communities such as WRF, Ginkgo, and others. So I would definitely say that I have a deep passion for open source work and enjoy very much being involved in open source communities. Lately, in the past few months, I've joined NVIDIA, where I serve as a principal software architect, mainly working on the networking stack and optimizing it for complex HPC and, of course, what's the hottest topic right now, which is AI workloads. So let's start with a short background regarding what CFD is. I guess that most of you, as part of your computer science or electrical engineering studies, didn't really hear about CFD up until today. So I'll briefly explain what CFD is. So CFD is the science of computational fluid dynamics, and it actually deals with simulating fluid flow, both air and liquids and other types of fluids, and also the associated phenomena. Associated phenomena can mean chemical reactions such as combustion, and other phenomena that are deeply associated with fluid flow. But specifically CFD, the C refers to computational. So fluid dynamics is a science by itself, which involves many methods, but we're specifically interested in the computational fluid dynamics, which means how to simulate fluid dynamics using computational methods. So this field of CFD is really very, very advanced. It started back in the, I guess, 70s, like more than 50 years ago. It started with very modest efforts by NASA and others. And it was mainly from the aerospace community. But ever since it started then, it branched out to several applications. Some of them you can see here on the screen right now. So if we take a look here, then we can see several representative applications that currently use CFD as part of their design process. One notable application that is also the focus of this SCC task is race car aerodynamics. So almost all Formula One teams now use CFD and specifically OpenFOAM to optimize the aerodynamic shape of their vehicles to reduce the drag and other aerodynamic effects and to get better performance. And this is now considered a very challenging task because there's not much room to optimize, but still there's a lot of effort and dedicated people that are working to try to optimize using CFD. In sports, such as the design of helmets for bicycles, for bikes, then this also shows you a representation of what a simulation of CFD can do. It can simulate the flow streaks and the shape of the flow following the body of the bike rider in this case. And it can enable us to test various designs of helmets, various designs of wheels, and how they affect the flow and as a byproduct, the drag or the resistance of the configuration to flow of air around the body. And this, of course, translates to better performance and better results in bike races. Some more complex applications include combustion. For example, here we can see an example of very complex flow that arises when there is hypersonic flow flowing over a cavity filled with fuel. So you can see here in this cavity fuel that is at rest, but when the high-speed flow of air flows on top of it, it combines with the fuel, mixes with the fuel, and ignites, which serves as the basis for hypersonic scramjets and generally combustion at high speeds, which is different than combustion at low flight speeds. So here you can see an example of a detailed CFD simulation that really goes into the details of the mixing of the fuel and the air and how it ignites and combusts along the path of the flow of air. On the left, on the bottom left, we can see the last example that I've showed here, which is medical research. So now, when doctors and other medical researchers design stents or various medical devices that are intended to go into arteries or directly into the heart, they use very heavily CFD to simulate the flow of blood in the arteries, and this way try to predict beforehand how this valve that is installed in the heart would behave when installed in the human body. And this is, of course, very beneficial that you can test it out before doing experiments on human beings. And I hope this gives you some sense as to how powerful CFD simulations can be and how wide they can be used, how widely they're used today. So moving on, now that we've seen what it can do, let's see how it's actually accomplished. So the basics of CFD is solving the Navier-Stokes partial differential equations. So I'm sure all of you have already studied partial differential equations and ordinary differential equations. So the Navier-Stokes set is a specific set of equations that was formulated more than 100 years ago by two people, Navier and Stokes. And these equations, this coupled partial differential equation set, actually formulates the equations that govern the flow of fluids by conservation of mass, momentum, and energy. So basically, these equations solve for a conservation of several quantities, in this case, as I mentioned, mass, momentum, and energy. And by solving these equations, we can describe completely the flow of fluids along a specific flow domain, which involves a body and the surrounding medium. So this system is very complex. It's a system of nonlinear partial differential equations, which has no guarantee that there is even a solution for arbitrary conditions. It's actually one of the open questions that is studied, and there's still a challenge with $1 million prize to prove that there is a solution to the Navier-Stokes equations and a unique solution for any given condition. This is still an open question if you want to tackle it in your own free time. But what we aim to do in CFD is try to find approximate solutions to it in various types of approximations. So the first level of approximation comes from discretizing the equations in space and time. What does that mean? So instead of looking for a continuum, meaning like an analytical solution to these equations, we discretize our environment into discrete points in space and in time. And this allows us to formulate the problem as a subset of smaller problems that, for example, as shown here, if we define a small control volume, then if mass is globally conserved, then mass has to be also conserved in this small control volume. And this allows us, by formulating the Navier-Stokes equations for this small control volume, we can break down the solution of the equations to a set of many solutions for all the discrete cells that are shown in this picture that actually include all of our domain. And as you see, for example, in the race car here, it also includes the body of the vehicle. And by using discretization in time, we can also, instead of attempting to solve for the evolution of the flow for infinite time, we can linearize the problem and solve for small increments in time. These increments are typically orders of milliseconds or even microseconds in some cases, where during this period of time, we can assume that the equations are quasi-linear. And therefore, this enables us to adopt another level of approximations that simplify the solution of the equations. So that's about as deep as I want to get into how CFD is actually done. If you're interested in that, then there's many opportunities to study CFD, both in terms of computational methods and also the numerical part of it. It's a very interesting topic, as I mentioned, which is very close to heart, but this will not be the focus of our task. We're not going to develop CFD methods. Instead, we're going to look at how to effectively solve this coupled equation sets after discretization in an efficient manner using OpenFOAM, which is a CFD tool. So that brings me to the question of what OpenFOAM actually is. So OpenFOAM is the most popular open source CFD software now in the world. It's also the #3 CFD software worldwide, only surpassed by Fluent and StarCCM. So that means, it's very unique that there's an open source software that is so highly ranked in terms of user base and applications. So this serves to emphasize how important this software is. It's used by a large number of academic institutions and industry, especially in Europe, but also outside of Europe. Two examples that I chose to bring here is that Audi and Volkswagen, which are two very big car manufacturers, use exclusively OpenFOAM for designing and testing their vehicles, all of their vehicles. And as I mentioned, nearly all Formula One teams, Formula One is, for those of you who do not know, is probably the most important race car race in the world. So nearly all Formula One teams use OpenFOAM for optimizing their race car performance. So this just gives you a sense of how important this software is. However, even though it's very widely used, it's still not optimized for heterogeneous computing, which is kind of strange, I would say. But there are efforts underway currently to optimize it for GPU as well. But for us, currently, it only supports CPU, the main branch of OpenFOAM, mainly because it's open source and developed mainly by the open source community. It's currently only supporting only CPU execution. Sorry. There are efforts underway to port OpenFOAM to GPU, but there is no official support yet, and therefore in this task specifically, we will focus only on the CPU execution. What does OpenFOAM suffer from in terms of performance? So first of all, like a lot of CFD solvers, OpenFOAM is also memory bandwidth bound. For various reasons that I will not go into right now, it has very low computational intensity, meaning that the number of flops that you have to, the number of computational operations that you need to do for every byte of data that you fetch from memory is quite small. And therefore, it is memory bandwidth bound, like many other HPC applications. And that, as you will hopefully see in your simulations, poses some strict problems in terms of intranode scalability when we reach that memory bandwidth bottleneck. The second thing is that its heavy use of linear solvers poses a performance bottleneck at large scale. I don't think that you will face this bottleneck in your simulations here because of the relatively small scale that we are focusing on, but just know that this is indeed something that hampers its scalability, specifically when we go to a large number of nodes. The last point is that I already made was the insufficient use of accelerators. So the fact that it does not effectively utilize GPUs really limits its performance today. And there are various reasons as to why this is not straightforward to port OpenFOAM to GPU. I will not go into them, but this is currently a very big Achilles heel, so to speak, of OpenFOAM that is trying to be addressed by many people. Another thing that you will not go into in this challenge, which is the I/O bottleneck of OpenFOAM. We specifically try to remove I/O from the simulations that you will be doing and not measure it, but just know that OpenFOAM is not really optimal in the sense of the use of parallel file systems and parallel I/O. And this is also another region where there is active research being done to improve its performance. So OpenFOAM as a big and widely used code has a very vast history. It started somewhere around, I think, the late 80s, like 89, I guess, as an academic code, which was developed in Cambridge, in the UK. And ever since, it grew and became and was forked several times. So it started as an academic code, and then the original people that developed it in the academy had some, how to say, they didn't agree on some things, and therefore, I would say each one of them opened his own fork of OpenFOAM. I won't go more into details as to the history, but it's quite interesting and has its own Wikipedia entry. If you're interested in that, you can read about it. It's worthy of a Game of Thrones episode, I would say. But right now there are three leading forks of OpenFOAM, or three versions, mainstream versions of OpenFOAM. One is the foundation version, which is maintained by CFD Direct, and it's called openfoam.org. The second one is led by a company called OpenCFD. It's actually a commercial company that lives from providing support and maintaining standard releases of OpenFOAM, even though OpenFOAM by itself is open source. It's a model that can be found in other software as well. And the third fork is Foam Extend, which is a fork maintained by another company, also by one of the founders that originally developed the code in the academy. And this is a fork that is mainly used for testing bleeding edge R&D or state-of-the-art developments before they are merged into the mainstream OpenCFD version. So for us, we are interested in high performance, and therefore we choose to employ the industry standard openfoam.com version, which is led by OpenCFD, which is the subsidiary of Keysight. So keep in mind that this task should be run with the openfoam.com version, and specifically with the specific version which is 2412. So this case that you are given was tested with this version, and we highly recommend to run this case with this version. Okay, so briefly about the computational architecture of OpenFOAM and what we need to know before we dive into the task. So OpenFOAM, as I mentioned, as many other CFD codes, discretizes the computational domain into small cells. In this case, these are polyhedral unstructured cells, which are shown here, and attempts to solve the Navier-Stokes equations in each one of these cells, and stores the solution at a representative point in the center of this cell. The way that it solves the equations after discretization is using an implicit pressure-velocity coupling scheme called SIMPLE. It's also a very well-known algorithm that is used by many other codes as well, but OpenFOAM has an efficient implementation of it as part of its source code. And the solution of this algorithm yields the quantities that we are interested in for each one of these cells, namely pressure, velocity, and other quantities of interest that enable us to simulate or visualize the flow around the vehicle or any other body of interest. So more relevant to our interest is how is this code parallelized? So currently, OpenFOAM is only parallelized in pure MPI mode, meaning that there is no shared memory parallelism, and the only parallelism is pure MPI. So the way that it does it is that after we discretize the problem, the computational domain is divided into several chunks as the number of physical cores that are, or ranks that are used in our simulation. And each core gets assigned a subset of the computational cells that needs to be solved. And there are various forms of how to distribute the cells between the cores in order to ensure load balancing. And you will experiment with some of these methods in the bonus task here. But basically, keep in mind that the parallelism is only purely MPI, which means that there, even if core 0, 1, and 2 sit in the same node, and they have access to the same shared memory, in terms of the execution of the software, each of them run their own process and has exclusive access only to its own memory, such that any communication at the interfaces between the cores has to go through message passing, and there is no optimization for shared memory. Again, there are various reasons as to why this is the case, and I won't go into them, but it's important for you to know that when you experiment with different performance optimizations. So every OpenFOAM simulation expects to have 3 mandatory subdirectories. And they are listed here. I won't go into each one of them. I'll just mention that there are key configuration files that you can and should modify as part of this task. And they all reside in the system folder. And one of them is the control dictionary. Dict is short for dictionary, and it controls the time and write intervals. And as you will see as part of the guidelines of this task, we ask you to reduce the time that we simulate in order to make the computational effort reasonable and not overtake all the resources of the cluster. And we also ask you to modify the write intervals, meaning what's the resolution in which we write the solution to disk in order to also enable us to visualize the results. The second key file, dictionary, is the decomposed power dictionary. And this one controls how the domain is splitted and how the cells are distributed among the different participating processes. And this is one configuration file that you can experiment with and to see its effect on the performance of the parallel simulation. So in this task, what we ask you is to to traverse all the main parts of conducting an OpenFOAM simulation. The first part, the preliminary part, is to build OpenFOAM from source. And the reason that we ask you to build it from source is to make sure that it is optimized for the target cluster that you are using. This is standard practice when we try to extract the maximal performance out of the code. The second part is to set up the case, set up the test case by modifying the configuration to accommodate the cluster environment. And David has already done some of that work for you by adapting the SLARM script to fit the Iris cluster, but you will still need to do some more changes according to your requirements. So the second part is running the simulation. And for that, you will have to execute the shell script to submit the job to SLARM and change several parameters, such as the number of cores that we utilize, the number of nodes, which MPI version we are using, etc. Then, after you've mastered the basic parts of setting up the simulation and running it, we ask you to try to optimize it, to tune it, to get better performance. And finally, we also ask you to experiment with analyzing the results. So analyzing is in several domains. One is scalability. We want you to analyze the scalability of the code for up to 4 nodes. The second one, we want you to extract what are the main functions that utilize MPI communication. And the third one is to visualize the results and to produce nice plots of the flow field around the vehicle. So actually, before I dive into the specific test case, maybe it's a good point to stop for a second if there are questions, and then we can continue on. So are there any questions regarding OpenFOAM in general before we dive into the specific task that you wanted to ask? No? Okay. That's great. Yeah. Okay. So for the test case itself, so the test case we chose is one that was extensively studied in several workshops. One of them is the Auto CFD workshop. There's a dedicated workshop for enthusiasts that test the suitability of CFD methods for simulating automotive aerodynamics, namely the flow of air around automotive configurations, both commercial cars and also race cars. And it was also studied extensively in the OpenFOAM HPC challenge, which I co-organized. And therefore, I'm very well acquainted with this test case. And I also provided a link here to reference results that you can also use as a sanity check for what you obtain. A full OpenFOAM setup of the test case, including the mesh file, which means how the cells are distributed among around the body, the physical model, and the solver that is used is given to you as part of the starting point for this task. You can experiment with it and change it, but we do ask you to consider the output that you're receiving, meaning that there are reference numerical results available from various sources. Among them are the Auto CFD and also the OpenFOAM HPC challenge. And when you experiment with whatever you choose to experiment with as part of this task, we do ask you to always keep in mind that the results that you obtain eventually are ones that are reasonable in terms of the physics. And when I mention the physics, I specifically mean that there are reference results or expected values for the drag, lift, and side force coefficients, which are marked in CFD by the letters CD, CL, and CS. And these coefficients were measured for this configuration and for this specific test case, both experimentally and numerically. And I do ask you to keep that in mind when you experiment with the solver settings and you find new and exciting features. Do a sanity check and test that the results that you obtain are ones that are reasonable in terms of their agreement with the experimental results. So what we do ask you is to reduce the number of iterations. The baseline setup of the case includes roughly 3,000 iterations, meaning that the time that we try to simulate is in the order of 3,000 time units. And we do ask you to reduce the number of iterations to only 300 iterations in order to, again, being able to squeeze your jobs within the limited resources of the iris cluster. So for tasks 1 to 3 in this SCC OpenFOAM task, we ask you to use only 300 iterations because these tasks are only measure performance. And since each iteration is identical in terms of the computational effort that it requires, it's enough to only do several hundred iterations. And you don't need to simulate the case from beginning to end. So this is for tasks 1 to 3. But for task 4, which is the last one, where we ask you to produce nice visualizations of the flow around the car, we do ask you to run at least 1,500 iterations in order to obtain reasonable results for presentation. Keep in mind that the simulations do not converge to a true steady state, meaning that you will probably won't get to a point where these coefficients that I mentioned before that represent the overall flow around the car reach a plateau. Instead, you will have some kind of noise like this, and this is acceptable and reasonable, and it's expected for this type of flow that includes a massive separation due to the configuration of the car. So what is typically done is that when we report results like this, we average them based on averaging a certain period of time after the results reach a quasi-steady point, such as shown here. This we call a quasi-steady behavior, where the values of a specific coefficient fluctuate around some kind of mean value, and we attempt to average them and report that mean value. Just to give you some sense as to what to expect here, this is a reference result that was obtained from the repository of the OpenFOAM HPC challenge, in which several institutions and several people studied this exact test case that you are also studying. And they have reported for different configurations the scalability results, meaning how much time it took to run the full test case. This is time to solution, meaning to run the full 3,000 iterations on varying number of CPU cores. And here, keep in mind that CPU cores is different here because each one of the configurations includes different number of cores per node. But several things of interest that we also expect you to see is that, for example, all the configurations reached the scalability limit of intranode, meaning that once we utilized all the cores on a given node, we reached the memory bandwidth limit. And this limit was manifested in the fact that even though we increased the available computational power by allocating more CPU cores on a single node, we didn't get any improvement in performance. And we do expect you to see that as well, and analyze that as part of your analysis of scalability. And as I mentioned, this part of multi-node scalability, you will probably not get to the point where the communication becomes so dominant that we reach the multi-node scalability limit. But if you do, it will also be interesting to see. But we do expect you to produce plots similar to this one when you analyze the scalability of the code. And we do expect you to look at the reference values obtained in this challenge, for example, and see that the results that you obtained are reasonable or in alignment with what others obtained. And if not, try to analyze and report what's the reason for the discrepancy that you see. So now more in depth as to what we expect to see. So we expect to see several things in your final submission. One is your best result of running the simulation on 4 nodes of the iris cluster. And in this case, we want to see results for 300 iterations, and we want to see wall clock time, not any other metric. Wall clock time is measured directly inside OpenFOAM, and it's called clock time. but you can also measure it with any other method of your choosing. The second thing we want to see is that scalability plot that I showed before, both for the standard configuration that we supplied and also for any optimizations that you may have found. The third thing is the analysis of MPI usage. You can use any MPI profiler that you like. We do recommend MPIP. It's a lightweight MPI profiler, but any other MPI profilers would also do the job. And we do want you to analyze what functions and what type of MPI functions are most used in this simulation. The last thing we want to see is the simulation results for a quasi-converged case. And that means, and this is in the following form. We want to see some nice images showing the flow around the car. And you can also look at the reference results that were presented for this test case in the OHC challenge. And also we want you to extract the evolution or the convergence of the drag coefficient of CD from the log file that the simulation produces. And to show that as shown here, that the drag coefficient converges to a quasi-steady state behavior after 1500 iterations. We do expect you to, as I said, to do a sanity check and to compare your results to reference results from OHC1, and you can see they are easily obtainable once you enter the GitHub repo that I linked in this slide. And we do have some constraints just to keep you, just to reduce the exploration space for you, and not because there are infinite number of things that you can explore, but we do want you to keep using the simple scheme that I mentioned before, meaning that we do want you to use only SimpleFOAM as the solver. We do not want you to change the mesh, meaning we do not want you to change the number of cells or use a finer or coarser mesh. And we do not want you to change the physical and numerical models that are defined in FV schemes. Just because any one of these things would lead you to an infinite exploration space, and we want you to focus mainly on several parameters related to performance. Meaning that for this solver and for these schemes and for this mesh, try to change other parameters that would affect the performance. I hope that's clear. That's it from my part. If you have any questions, then I'll be happy to answer them.
Thank you, Mark. It's open for questions if anyone has one. In any case, we encourage you to use our Slack channel and ask a question in the team channel. Yes, Tobias.
Hi, asking the same as always, are we allowed to use compiler options that can affect the accuracy, something like OFAST?
Yes, I think you can try to compile OpenFOAM with different there is a baseline script that David provided for you, but you can try to experiment with different compiler flags. But we do want you to, when you report your results, we want you to see that the results are in agreement with reference results obtained. So for example, these are the reference results for this test case in the drag, lift, and side coefficient. So if you change something, we want you to test that it doesn't produce garbage. Okay?
Okay, thank you.
Yeah, any more questions?
Okay, so again, if you have probably only the beginning, so if you have questions as you go, feel free, don't get stuck, ask us, and we'll try to help and try to experiment, again, utilize the clusters. Most of the time, you all should have access to the clusters now. Again, if you have any issues, let us know. connectivity issues or any other issues, and try to utilize all the time that you have, about a month and a half on the clusters, and to run the applications.
Yeah, Tobias had another question. Yes, Tobias?
Tobias, go ahead.
I wanted to ask if you already know for the task for the in-person competition, if we also only use the CPU version, or if there's something else that does or does not apply for the in-person task of the things that were said in this talk.
I don't know. I don't think we have decided yet on the in-person task.
So normally we have different tasks for the in-person GPUs and CPUs. In many cases, we don't, we don't care. I mean, you can try to run it on GPUs if that helps on your runs. OpenFOAM specifically, as Mark mentioned, is not fully tuned for GPUs, so we didn't aim for it now. But I believe that within a month or so, we will, have internal discussions to see what we can do for the in-person task, and I will announce this as soon as we have the idea. It's still slightly early, so stay tuned. Okay.
All right. Thank you.
There's another question from Katrin about task 1. Mark, do you see on the chat about the
No, I don't have the chat. Catherine, can you say your question out loud, because I don't see the chat here, or I can try to open it.
Yeah, try to open it on the chat box.
Let's see if I can access it.
I'll read it.
Okay.
You
I can see it. That's okay. Yeah.
Okay.
When submitting my best when submitting the best result, yes. When submitting the best result, you can change whatever you want. Yes, but we do expect you to accompany it with some kind of measure that the results are reasonable in terms of accuracy, or in agreement with the reference results. But yeah, specifically the composition that you asked about, Catherine, yeah, you can report results with different decomposition methods in task 1. So you can try to use different versions of OpenFOAM as well. We provided the setup, and we know that it works for 2412. We haven't tested it extensively with other versions of OpenFOAM, but you're welcome to try it out and experiment.
I will add that if you try another version of OpenFOAM, maybe compare and submit both results, so we can see if there are any differences. But we don't want to restrict you if there's no real reason. So if you want to experiment with other version, it's possible. And again, as Mark said, we tested it on 2412, so we know it works there.
Yeah, but feel free to experiment according to your availability and what you see best. I'm really interested to see what you guys can come up with. Maybe I'll learn a few things as well.
Of course, you will. You will see. Okay, any more questions, everyone? Again, feel free to use the Slack channel. If you want to, if you need to, we are here to help you to, utilize all the time on the clusters and enjoy the process. And again, I think we can go for the closing. So I want to thank Mark for the presentation, and I'll post all the recordings from today later on the wikis and on the main channel on the Slack. Okay, and keep keep checking the Slack for announcements. Okay. Okay.
Okay.
So
Thank you, everyone.
Okay. Bye-bye.
Bye-bye.